Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Welcome back in lecture 14. Basically, in this lecture, students, we are covering some other examples, okay, on same beam analysis, steel beam analysis and design. Here you see flexure deflection of beams, okay. So it basically belongs to serviceability, and I explain all those terms, okay, and theory in my lecture number 11. From lecture number 11 to lecture number 13, I explain these limits, okay. I explain these limits, and let's see, we do an example. Remember, these are the Professor Dr. A. Verma notes available on Google, okay. You see, design a simply supported beam subjected to uniformly distributed dead load is given, and a uniformly distributed live load is given. The dead load does not include the self weight of the beam, so that's why you have to include the self weight of the beam. How to include? Let's see. Steps 1 is same, you already know this. The beam is simply supported, a live load this much, dead load this much, okay. You just need to factor them in, find out the moment capacity, that is your MU, okay. Now select the lightest section from the AISC manual design tables. Clear? From page, you have to need to write down that page of the AISC manual. Select W1626 made from 50 KSI steel, okay. We have assume 50 KSI, okay, not given, but we assume, okay. You can assume, okay. Now the capacity of that section is pi b MP. If you have an AISC manual, it is a simple approach. You need to select such section which have a capacity, you can say, more than or equals to this much. So in ZX table, and if you search this section, that is W1626 section, which is just in front of me, where it is 1626, I think so, this one 1626, yeah, 1626. So 1626 is this section, and you see the capacity of this section. This is this one, okay. And make sure you are in this table. You see the capacity is this one, 166, okay, 166. We basically this V in ASD method, so we don't care for that, okay. Now the capacity is how much? 166. From directly we select from table. If you don't have AISC manual and you have LRFD manual, this one LRFD manual, the approach is simple. I explained this approach in my lecture number 1. Please visit that lecture, you will understand. If you don't have this manual, this one AISC, then how you can use this LRFD manual? Clear? So please revisit this lecture, sorry. Add self weight, you have to design section and check. Now 26, this is the weight of the section, so you need to add it. Now the total dead load will become more larger, and you need to again determine WU, then you need to again determine your MU, and you see this is a good news for you. If you add the load, that is the reason that whenever you are select such a section whose capacity is a little bit larger than the required one. Although we need 160, we select such a section have a capacity 166, a little bit larger than the required. So that's why if we include the self weight of the beam, you see it doesn't affect, although we are on the safe side. So that's why our section is okay. Now the section is okay, the section is perfect for movement capacity. Now the question is that whether it will pass the test of deflection. So for that purpose, they calculate the service loads. these are the total deflection at service loads. Okay, so this one is, I think so, the UDL, and yes, okay, 0.026, 0.55, I think so, these are dead loads. Where it is, this one, yes, the first one is slab distributed dead load, the third one is a live load, and the middle one is the dead load also, that is the self weight of the beam. Okay, this is the total service load. They just find out the deflection. Okay, and the deflection is 2.142 inches, which is greater than L by 360. So that's why it basically it doesn't passes the limits. Okay, because it is, you can say it is beyond the limits, it is outside the limits. So that's why we have to redesign the section. So in lecture number 11 and 12, I explained the steps that whenever you have to design in an analysis of a beam section, you need to come with a selection of a section by IX. You know, I explained the steps. You need to calculate this IX, which you are see here. Fix a deflection value, that is L by 360. Find out this L by 360, plug the value of L by 360 here and find out IX. Go to the IX table and choose such a section whose IX is equals to or larger than this one. Clear? So that did the same step. L by 360 is 1 inch, which is greater than 5W, this one. So they find out IX from that formula as we did in lecture number 11. Now they go to the IX table, which you see here. Okay, right there. IX table is just below the ZX table. Here you see. And there is IY and IX tables. Okay, here you have to choose such a moment of inertia, such a section which have a moment of inertia larger than what? Larger than that calculated one. Clear? Larger than this one, 644. So they search a section W21 cross 44. Okay, W21 cross 44, where this section is. W21, W21 73, W21 68 and 57, 50, and this one, the most latest section. Remember, this black bolts words representing that these are the most lightest section. And you see IX is, you know, at 143. So that's why you see here at 143, and its capacity is 5 EMP is 358. From where this figure comes. So for that purpose, you need to go to ZX table in the same LRFD manual and find out its strength. Okay, or if you have a AISC manual, you need to go to this table where you have W21 44 section, I think so, where it is 21, this one, this is 55, this is 48, and this one, I think so, this one. Okay, let me check. Yes, 44. So you see the capacity of such section will be this one. Okay, and remember, make sure you are at the right table, and here you see 358. Clear? So this how you see 358. So you covered the deflection as well as the moment capacity. So that is the approach basically for such kind of questions, that whenever you are dealing with serviceability criteria, you need to come with another approach, not just the approach which we explained in lecture number 1, that is the ZX approach. Okay, note that the serviceability design criteria control the design and the section both. This is important. Here you see in another example, design the beam shown below. The unfactored dead and live loads are shown in figure, and the beam length is 30 feet, 15 feet there is a point load which is live load, remember, and the unfactored dead and live loads are shown here. Okay, the dead loads, live loads are shown here. The steps are same. You need to find out WU. Remember, there is dead load, live load. Okay, you need to find out PU. PU is this one. Clear? And then you have to add up what 1.2 PD. Okay, and PD is 0. Remember, PD is 0 because there is no PD. You just see live load. And PL is basically what? PL is basically this one. Okay, PL is this one. So you just insert the value. Okay, and you just need to insert the value and you got the answer, that is 16 kF. Clear? I think so. This is not tricky. Basically this is important because the beam is subjected to UDL as well as the point load. So the movement diagram, because you have two movement diagrams. Okay, the one is for UDL. Clear? The one is for UDL, which is WU L square divided by 8. Clear? And one is for point load, which is acting at the mid. Okay, so that's why the point load maximum movement will be PU L divided by 4. Clear? So you need to add up these two movements, remember. So that's why basically your MU is 344. Okay, select the section. That is an easy step. Go to the table. Okay, and find such a section. Okay, here F for example, you are using this one. Come here, find such a section having MPX such value which is more than 345, round about 360, 350, 355. Okay, when they go to the table, they select a section W2144 for 50 KSI. W2144, let me check it. W2144, this one, the same section 358. So this section will also work here. And 5E, this is 358. So this is greater than MU. Okay, self weight is this much. Now include this self weight in here and you redesign the question. Okay, so this is the step. You need to redesign the things, the same WD and the same WU. Clear? And remember, in PU you don't need to add up. Okay, because the weight of the beam is uniformly distributed. So that's why this 44 should be add up with what? With dead load, which is coming this one, 0.67. Okay, so you must remember. Okay, this is 0.044. Clear? And then you need to add up your live load. Live load is 0.75. So this is the way that how we can you see the total dead load basically, which is UDL, this much, and total dead load, factor dead load. Now you add up these two dead loads and you got the answer. And then you see here, okay, this is WU L square divided by 8, and this one remains still same. Okay, so the capacity, you see it is less than pi b MPW8. Okay, still okay, because we see our design capacity is 358. Okay, 358. The section which can support basically a design capacity is 358, and you see here this one. And now the factor movement is still this one, so the factor movement is lower than that one, so that's why here we are on the safe side. Now, but if they check for the deflection, for service deflection, okay, they find out the distributed loads. See, dead load, live load, and then the concentrated loads. Remember, here live load is 0 because you see here we don't have any, we have live load but we don't have dead load, so that's why PD is basically 0. Okay, but this is PL. Clear? So you must clear these points. Okay, dead plus live. So dead is 0, PD is 0, but PL is 10. So that's why we have 10 kept. Now, deflection due to uniform distributed load. Remember, uniformly distributed load, okay, give you a deflection. For example, if you have a beam and it deflects due to uniformly distributed load, this is your deflection, okay, delta. Due to UDL on a simply supported beam, the deflection will be calculated by this formula. But when you have simply supported beam and it is subjected to a point load, when it deflects, its amount of deflection, the formula which is used for this amount of deflection is this one, PLQ divided by 48 Ti. Remember, this is due to concentrated load. Delta C concentrated, delta D is basically distributed load. So the total deflection will be the summation of these two. Remember, the summation of these two. Now once they calculate the total deflection, total dead and live load, service deflection, remember, not factored, it comes out to be 1.49. When it compared this with the limits L by 240, you see 1.5. Here we pass basically. Okay, you see the deflection is lower than the maximum and the section is okay. So this is good news for you once you pass this test. So at the beginning of the lecture number 11, basically, this is a good information for us, that in the beginning of lecture number 11, I already explained that if you select a section on the basis of ZX approach, it may pass, almost it failed, but it may pass sometime the section which in deflection criteria as well. And you see the result. Although we selected the section on the basis of ZX and they pass the reflection test as well, but they are very close. Remember, it's very close, 1.5, 1.5. Okay, so you will be lucky in this case. But always, if you select the section on the basis of IX, they always pass both the test. And you see the author also write down that step as well. Here you see, and I already explained this basically in my lecture number 11. So the IX approach is basically, you can say, a good approach. It's this is the end of this lecture. Okay, and see you in next lecture. Okay, if you have any question, any suggestion, please share. Thank you for watching.